Hello everyone, I'm Steven and you're watching Steven Loves Science, and in today's video we're going to learn how to use an ice table. So thus far we've been talking about equilibrium. We've been talking about the equilibrium constant KEQ, defined as the ratio of the concentration of products divided by the concentration of reactants. So let me ask you a question. Let's say we have a reaction that we know goes to equilibrium, and let's say I have a certain concentration that I'm beginning with of reactants, and I want you to tell me my end concentration, my equilibrium concentration. Well, how can I do that? Well, I can do that using my equilibrium constant and something called an ice table. So before we get any more confused, let's try to start with a problem. So here we have an example problem that says initially for the reaction below, the concentration of hydrogen and iodide are 0.2 molar. So let's just go ahead and plug that into our table. Right now, this is all just magic happening. So hopefully it'll all make sense at the end. So 0.2 molar for hydrogen, 0.2 molar for iodide, and these are our initial concentrations of stuff in our reaction. So if the reaction hasn't started yet and this is the initial concentrations of everything, the reaction has not started yet, so what should our concentration of HI be? That's right, it should be 0. So in our earlier videos on equilibrium, we've talked about the fact that reactions don't start at equilibrium, they have to get there. So I drew this little scale, and I said in the beginning we're going to have a lot of reactants and not very much product or 0 product, and a change is going to happen. We're going to lose reactant to make product, and eventually our scale is going to look nice and something like this. So we know that we have to lose product. How much product we're going to lose? I don't know. So that'll be our unknown. We're going to make it negative x, and the same for iodide. We're going to lose iodide. We don't know how much, negative x. And how much HI are we going to gain? Well, we know that we lose 1. There's an imaginary 1 in front of here is our coefficient. Imaginary 1 in front of here is our coefficient. And there's a 2 here. So we know that for every 1x that we lose of H and I, we're going to make 2x of HI. Isn't that nice? 2HI. 2x. So what is our equilibrium? Well, we know 0.2 minus x for this one. Bam. Minus x. 0.2 minus x, because we're going to lose some of our concentration. And 0 plus 0.2x, so let me put a plus sign here, is going to be plus 0.2x. So, when we first started the video, I said that our equilibrium constant is going to be involved in here. What do you know? The problem gives us an equilibrium constant, KEQ. So what is the equilibrium constant? It is the concentration of products at equilibrium divided by the concentration of reactants at equilibrium. Oh, what did we just do here? We have a nice little E that tells us the concentration of our reactant at equilibrium to be 0.2 minus x, and our concentration of product at equilibrium is positive 2x. So that means we can substitute in our values that we obtained using the icebox into our equilibrium expression. So that means 64 equals KEQ, so KEQ equals 64, and we know that in order to get 64 we have to divide the concentration of products, which in this case is 2x, over the concentration of reactants, which is 0.2 minus x for both of them, so squared. And we know that when writing equilibrium concentrations, we raise the concentration to the power of the coefficient, and in this case the coefficient is 2, so we're going to raise it to the power of 2 here for our reactants, for our product, excuse me. And then we want to go ahead and solve this equation for x. Well, it is very easy since both of these are all squared, and the square root of 64 is 8. It's not going to be like that in all of them. In our later videos, we're going to learn how to use the quadratic formula to solve these. But we can go ahead and take square root here, bam. We have 8 equals 2x over 0.2 minus x. We do some simple math, and we find that x equals 0.160 molar. So we know that x equals 0.16 molar. So we want to plug these back into our equilibrium values here. So we know that at equilibrium, the concentration of H2 equals 0.2 minus 0.160 molar, which is going to be, I guess, 0.04 molar, I'm pretty sure. And our concentration of iodine is going to be, we're going to be doing the same thing, 0.02 minus 0.061 equals 0.04 molar. And our concentration of HI, which is our product at equilibrium, is 2x, so that's 0.6160 times 2, 0.32 molar. And that is how you find the concentrations of products and reactants at equilibrium using an icebox. Thanks for watching this episode of Steven Loves Science.
La ciudad se llama Duke, Nuevo México el estado.